second talk of the evening, and Ifas Kabir will teach us more about programming with structural subtypes.
Thanks for coming, everyone. Before I begin, I want to talk about myself a little. That's why I have my favorite slide about me. So I'm also from the University of Waterloo. I'm a master's student there. I'm in computer science, and I am part of the programming languages group. And most of my research, or current research at least, looks at the dot calculus, which is a calculus that models Scala. And our hope is to kind of expand this calculus to the full language as much as possible and kind of prove that if you program in certain patterns in Scala, your program can never crash. Modulo some like other things such as like memory, if you're running out of memory or something like that. But other than that, like there won't be any exceptions or anything like that. So this talk is based on a paper. It's based on a paper called Programming with Polymorphic Variants, or at least most of this talk is based on this paper. And it's by this person whose name I'm not going to bother butchering, but the paper was for the OCaml workshop in ML. This ML is not machine learning. It's the programming language ML, and it's from 1998. So this kind of idea and everything is around 20 years old or so. So these are some old ideas, but hopefully new to you guys. So kind of moving on. If you go out and try and read more about some of these stuff, you may run into this phrase instead, row polymorphism instead of structural polymorphism. So that's something to be aware of. And this talk is going to talk about, or this talk is going to use some OCaml phrasing. And OCaml is a programming language that is a descendant of it's part of the ML family, so going back to the workshop in ML thing. And the phrasing that's going to catch you off guard maybe is variants, and they just mean algebraic sum types, or think enums in Rust, or case classes in Scala, or like more weakly unions in C, but you know it's a little weaker connection there. So moving on, we want to write programs that kind of are polymorphic over the structure or shape of data. So we want to write functions that work over lots of data of different shapes and sizes. For example, I'll start off with this example. So we have one record which has the name Lucifer and number mobile, and another record that has a name and an address of some sort called home. And we want to write this function getName that takes in a record that has a name and just gives you the name. And this kind of pattern is very common in dynamic languages or scripting languages. And at the very bottom of the code, I just kind of print out both Lucifer and Gabriel's name, but that's beside the point. So this getName is this is structural polymorphism for records. The getName function works over both Lucifer and Gabriel, even though they have different types, as in one has a mobile field and another has a home field. But this talk is not going to talk too much about records, although the first part is going to be talking about records. This talk will focus on variants instead, and we'll get to what variants are later on. So continuing on with records, this is what kind of typing for records kind of look like. If you see over here, if you have some hidden fields UI and you type some values AJ as as fields having these types, then you can create an object with methods having these types. Like I'm trying not to focus too much here, so I won't spend too much time on this slide or anything like that. But kind of just to give you guys a feel of how the type system kind of works. And with the previous slide, you can start typing things like this lambda function here that just gives you the name of a field or something. And the type ends up being that for every this lambda x dot x dot name almost, there are two different dots, so I'm using hash instead here. But over here, this function has the type for all A, for all row. If this has a name with a name field with the type A, type alpha, and some other fields represented by the row here, then this function will act on those inputs and give you the name back. So kind of going from records, I want to move on to variants, and this is what polymorphism over variants look like. So if you have a type called token, for example, and it can be either a string of some string or some other token, and you have a different type, AST node, and it can contain the same type of strings, but also some other things. You can write this isString function that can accept all of these kind of types, and whenever you give this function a string, it'll return true and false otherwise. So this is polymorphic over the structure of variants rather than records, and variants are duals of records in this sense. Records have fields, and variants can be these named objects, and that's kind of where the duality kind of comes in. Any questions so far? So in this example, there are AST nodes that are not tokens, namely other node, and there are tokens that are not AST nodes, namely other token. And did I say that right? Yes. And isString works over both safely. And these are the kind of programs we want to write, and for our type checker to say that it's safe to do so. Oftentimes, these kind of patterns show up in scripting languages, and like if you try and kind of port that to type languages such as Java, the type checker will just keep complaining at you rather than give you any solution. So, kind of moving on, these kind of patterns are somewhat similar, kind of show up in Scheme sometimes, so that's there, but if you've never programmed in Scheme or Lisp or anything like that, that's something just kind of like a side comment. Moving on to a more non-academic example, OCaml has this Oxygen web framework, and they have this TyXML library. And this library is interesting in the sense that any HTML that the library produces is guaranteed to be a valid HTML to the specification. And how did they kind of do this? And I'll just give you guys a brief preview of how things look in this library. And you have these covariant element types, and this covariance just means that if you have HTML and you have an HTML element, then how do I want to express this? This type parameter kind of varies in the same direction as whatever is kind of being filled in here. So if you have A and B, and A is a subtype of B, then an A element will be a subtype of a B element. That's what I'm trying to get at here. And the types kind of are very large, but I'm only kind of showing a very small part of this. So the HTML type will be this variant HTML, and HTML content will be this variant body or a head, and an HTML attribute will be either class, manifest, enclave, or something along that line. And you can build documents, and a document type will be an HTML element. And there's this constructor that takes in a head and a body, and it produces an HTML element. And since they hide enough things inside modules that you don't have access to, so that these things are guaranteed to be like to the specification. It's very hard to lie to the type checker about whether something is a valid HTML or not. And if I move away a little, where did Google Chrome go? Is this Google Chrome? I can't tell.
Okay. Yeah.
What's even on the screen?
Yeah,
It's just mirrored. Oh, okay, there it is. Just to kind of show off what the types look like. Did I click it? I can't tell. Is it working? I don't use Google Chrome, so I'm having a hard time. Let me just open up a new tab. So these types are very large. You're encoding the entire HTML specification into types. So someone went in and wrote out all these types, but now that they have done it once, you don't have to do it again. So when you're using this library, you don't usually have to worry about writing out types or anything. Things are all inferred automatically for you. So just to kind of give you the flavor of how, like, what things look like. So moving on.
How you verify that those types description are correct?
So that's kind of done manually. The descriptions. If you look at the GitHub repo, they only it's kind of code reviewed and say, hey, I'm adding this new feature. It's to this spec. And if they don't see that things relate to the spec, they'll reject the pull request or something like that. So there is like human verification at some point, but after that point, it's all just type checking. So if the library is correct, then it produces only valid HTML. But if there's a bug in the library itself, then you might be able to get away with some lies somewhere. So yeah. Okay, going on. So the paper that this paper is kind of based on, it adds these tags and these pattern matching to CoreML, which is a proven sound core of ML, and they kind of prove that things are sound, and since this is ML, they run into issues while trying to extend the type system, and the paper kind of talks about that. But I want to kind of focus on how variants are useful or used. And one of if you've ever programmed in Haskell, for example, or OCaml, you know that whenever you're using variants, you always have to name them and declare them. And with polymorphic variants, they kind of exist in the ether, and you can summon them whenever you want. So if I go back, I never actually had to declare token as being this type before I started using string and other token over here. So that's, I think, kind of interesting in the sense that this string constructor over here kind of exists in the ether, and you can summon it whenever you want. So this kind of leads to less declarations. And polymorphic variants kind of subsume regular variants in languages like Haskell, OCaml, or even case classes in Scala. They exist before you use them, so you can just summon them from the ether. You can use them in place of regular variants, and that's fine. So this is just kind of like side effect rather than you normally still want to use regular variants whenever it fits your purpose, just because regular variants have better error messages. They don't end up with these huge inferred types showing up in error messages, so they end up being a little better. But you can use them in place of regular, you can use polymorphic variants in place of regular variants, as long as, type safety is not being violated anywhere. And, but again, you should use regular variants if you can, because otherwise you get these horrible error messages. So going back to TypeXML a little, polymorphic variants allow you to have these overloaded constructors. So we can use the same constructor and it can adapt to several different types. So for example, what example do I use here? If you have many different attributes, you can use the same class constructor for many different types of attributes, both for example, list attributes and for text area attributes. And the class constructor in TypeXML kind of looks like this. It's just taking in some classes, and then it's producing this attribute. Polymorphic variants also kind of lead to these implicit data types, since they exist before you use them. It allows for creating data that is accepted by a function in a different module without, having to declare things first or import a module or anything like that. For example, in this example, I have in the poly version, I can just write down float, and any module that accepts this float, this type will be able to work with this data, whereas with regular variants or something, I would always have to import this constructor float somehow, rather than summoning it from the ether. So it creates this dependency between modules all the time. This one way is opening up a module and referring to a constructor in a module directly. Over here, I'm locally opening up the module and creating this value. And the last example, I'm globally opening up a module and creating this value. So these last three are creating the same value, but they're just a little more verbose compared to just creating this value in the first case. Moving on. Going back to the title of this talk, structural subtyping. This allows for structural subtyping, and I'll start with the example. Going back to the example earlier, the input type of isString, whatever the type is, I didn't declare it here, but it accepts both tokens and AST nodes. And so token is a subtype of this input type here, and as is AST node. And the actual type that isString takes is anything that can either be a string or other token or a node. And so that's the full type, but both AST nodes and tokens are subtypes of this input type. And you can pass in any value that is of type AST node into isString. And this type checks and everything, so everything is safe. What am I talking about next? As I kind of mentioned earlier, polymorphic variants allow for fewer dependencies. So over here, first and second do not depend on each other, or they don't even depend on some other module. They don't both depend on some other module that that they need to import these constructors from. So, but this third module depends on both of them. So this is kind of what the dependency graph is shallower than it would have been otherwise because we were using these polymorphic variants. Oh, I have a typo here. Whatever. No, I don't. No, this is not the constructor. This is just the module thing. Okay, yeah. No, things are fine. So oftentimes, when you're working with data and you have these functions that you write that cleans up the data a little bit, and then the resultant data will never have certain kinds of patterns. But if you've declared something to be of, say, some type, and it can either be some clean data or some unclean data, you always have to keep dealing with this unclean data part, and the types usually don't reflect that. But with polymorphic variants, things become a little nicer. So I sometimes work on a compiler for a language called Flix, and this is and the compiler is written in Scala, and this is an example from the code base, and so we do some cleanup of the syntax tree for programs, and after the cleanup, there should be none of these make closure lying around. But since we declared something as being a case class, and this can always be part of the case class, we always have to deal with it and throw an exception every time that we're pattern matching against expressions. But with polymorphic variants, things are a little nicer. So if you have things that can be either foos or bars, and you do some filtering, and you should only be left with foos at the very end, then after this function guarantees that it only returns foos, not foos and bars. So if you were using regular variants or algebraic data types in Haskell or something like that, this return type would also be foo bars. But thankfully, things are just like with polymorphic variants, you're guaranteed that you only return foos. So these kind of declared types don't hang around, and if you write them in specific patterns, you can guarantee that after some point, things can never be bars anymore. So that's a nice feature, I think. Any questions so far?
You mentioned at the beginning the inspiration of the talk from that paper where the author says that he can guarantee no crashes for a Scala program?
No, that's what I do in my day-to-day research. So that's kind of separate from what I work on.
Oh, okay.
And this is, the language Flix is something that my research group also works on, but it's kind of separate from what I am currently working on. It's just something I sometimes look at every now and then, and I have some commits in there, but it's not something I'm involved in a very major way. So. Okay, I wanted to talk briefly about how polymorphic variants are compiled as compared to regular variants and regular enums. For example, even in languages like C, so I have an example here. You have a type T, or think of it as an enum, and it can either be Alice, Bob, Charlie, or David, and you can write a function test B which takes in something of type T, and it returns a number, and when it's Alice, you return 100, and when it's David, you return 103, etc. And when you're compiling this, your compiler builds this jump table, and so when at the machine level it sees a 0, it compiles Alice down to 0, for example, And whenever it sees a 0, it returns 100, and when it sees 3, which is what David is compiled to, it returns 103. And if you write a very similar program for polymorphic variants, things that are a little different. Instead of generating these jump tables, we generate jump trees instead. And what does that look like? So these Alice, Charlie, Eve, Bob, and David, they're thought of as being strings, and then these strings are hashed, and then these hashes are kind of what we make our decision on. So if this value is not 300 whatever, then we do some more checks. Otherwise, we return 101. I guess this is the hash value for Bob, and similarly, other things happen. But the main idea is that we treat them as string hashes, and the reason why we do this is, what do I want to say here? So you may be wondering why we don't kind of keep these strings around, or why we don't keep, why we don't kind of use some sort of a counter kind of mechanism rather than kind of keeping track of these strings. And the reason ends up being that if you use a string hash, things are a lot more efficient. So checking against a number is very, very quick. And the reason why we don't use kind of like a counter kind of thing and keeping track of which string corresponds to which number, the reason for that is it ends up being that when you're in a separate compilation setting, if you're compiling one module that can have some Alice and another module that can have a David, you want to use these string hashes instead. So this seems to be the best way to go. And what happens in OCaml is in the linking phase, if there's some sort of a conflict between names, it gives you a compiler error. So that's kind of the decision they went with. It might not necessarily be the one you'd pick, but that's what they pick, and they've had good results in the language overall over this decision. So I don't think it was a particularly bad decision. And kind of moving on back to typing a little, we want to start typing things such as, we want to say that if you have some tag 1, which can contain some type ta1, etc., and you have some other type which can contain some more tags and some more types, then the one with this smaller number of tags is a subtype of the one with more tags. So we want to do things such as take the greatest lower bound of 2 types or least upper bound of 2 types to kind of build up the subtyping lattice. And we want to, if life was very easy, we would just take the intersection of the 2 lists of tags or take the union of the lists. But life ends up being a little more difficult. So this is kind of what we want. This, if true, then A, B, otherwise C, D. We want this to have A, B, C, D, or otherwise, if we have a function that takes in an A or a B and returns some Boolean, and another function that takes in an A or a C and returns a Boolean, these should kind of merge up to a function that can take in an A and returns a Boolean. So we're taking the least subtype of the input types A, B, or AC. And if we're only working with these tags, things work out very nicely. But as soon as we add tags that can contain other values, things get a little more crazier. Just because we're in a OCaml setting and these least upper bounds are very hard to compute. So if you have this example, for example, so this function f can take in some c and it should return a boolean, and so this is the function you kind of write down, and when you start asking things such as so this function takes in some c of some type A, and this function takes in some c of some type B. And when you try and compare A against B, since the types are kind of unknown and they're being represented by these variables A and B, we don't know how to kind of compute the least upper bound of these two types. And if we pick the least upper bound to be empty, then we miss out certain things, and if we take them to be one of A or B, then we can get other results if we somehow infer that A is not B at some point. And it's kind of related to how Hindley-Milner works in OCaml, and Hindley-Milner ends up getting in the way all the time. And Hindley-Milner is a sort of type inference algorithm, and it's what OCaml uses, and it's just kind of adding this to the language ended up being a little hard, just because the Hindley-Milner algorithm can't compute equality of types. It can only enforce it. And so the solution ends up being to kind of add these polymorphic variants to OCaml is to not compute the equality of types and to enforce them instead. And they have these representations of types, and they have a presence part of a type and type information part, so the left and the right parts. And they have this notion of a compatibility of two different types. And I'm moving over it a little quickly because I don't think the nitty-gritty is all that important, but kind of to see a concrete example, if E has some Boolean type, and you're trying to combine E1 and E2, and you're trying to kind of compute what the resulting type should be, then you take the union of the presence part of E1 and the presence part of E2, and you take the disjoint union of T1 and T2, which are the type parts, and similar things happen on the intersection parts. This is an example of taking an intersection here. Moving on. So again, kind of more talks about typing. You can combine the two things, this representation into an upper bound and a lower bound, and kind of represent it this way. And there's a notion of subsumption and subtyping, and wow, I should have removed this slide, but whatever, let's talk about it. So this is what the type syntax looks like, but kind of in a more formal setting. And well, I don't think there's any point in trying to figure out what the type rules are, but kind of they're here. I should have removed those two slides, but I forgot. And kind of once you have those type rules, you can start typing expressions like A with lambda XX, and you can type it as this thing, and something that pattern matches on some A, you can also type it as an expression. Oh wait, this is a full expression. And this returns the lambda here, so it has a type for all A to A. So I'm near the end of my talk, and kind of ending on polymorphic variants. Typing for polymorphic variants is very complicated, but it may be complicated in the OCaml setting specifically because OCaml has this inference requirement. But even if the inference requirement wasn't there, we would still have very bad error messages. So that's kind of the bad part of polymorphic variants. But I think there are some good parts. Firstly, I think polymorphic variants are very cool. They allow all these patterns that basically come from scripting languages and allow typed languages to type them and prove them safe. So I think that's kind of cool. But other than that, that's the end of my talk. Thank you for listening.
So you talked about types. I'm not very familiar with it, but is there something to be considered for function types that's different from value types? In the inference or in the kind of...
Functions have the type like if you have two types A to B and you have things that take in an A and return a B, then that's the type.
What if the value of the function is another function? So for metaprogramming.
So if the value of a function is another function, like the value of the return,
Yes.
if it returns another function, then it's just another arrow type, right? Like A to B, like or
So
C
it
to
goes
D.
all the way down.
Yeah, like you can represent almost anything using these types.
So then through that, you kind of get into a computation model, I presume. So then does like the Church-Turing thesis apply at some point? Like you're actually predicting the value of the computation, and what does that mean for it?
You're predicting what the you're predicting what, like, not necessarily what the exact value is, but what it can be. So if a function has a type int to int, for example, like, you're predicting that it takes in an int and it produces some other int. You're not actually predicting which int it is, right?
Okay.
So that's where things don't kind of break in terms of the church theory.
So you don't break the rules.
You're not breaking the rules, yeah.
Being able to make such guarantees, is this useful maybe also in automated theorem provers? Like to be used, like for example, like if you would use your research within Coq or something like that?
So kind of to put things into perspective, I do use Coq on a daily basis. That's what my main research involves. So okay, so Coq already has the guarantee that it can never crash in the sense that the system is like very normalizing in the sense that any computation you do in Coq will always end up producing a value. So like this kind of guarantee problems are so type safety is the notion that you can never crash, whereas Coq has a much stronger guarantee saying that you will always produce a value. So all that type safety says is you will either produce a value or you can keep computing, but it doesn't really tell you that you've computed the value. Any other questions, comments, concerns?
So this this variant polymorphic stuff, I understand, is supported by all like ML type of languages, yeah? Like Haskell, OCaml, Scala.
So variants in general are supported by Haskell, OCaml, and ML type languages, whereas polymorphic variants are very OCaml specific. So they were never really adopted anywhere else. And I think in Haskell there are ways to kind of encode some of these patterns in type classes, but I'm kind of not sure how they work out. So I won't speak too much to that, but there are some ways of kind of emulating this idea in Haskell.
So what about popular languages like Java or C#? What efforts are done there to improve code safety? Yeah?
Even OCaml in some sense isn't type safe in the sense that you can still crash a program. All that we guarantee in some sense is if you use a very safe subset of OCaml, then things are very sound and will never crash. So normally you write all sorts of programs and you kind of give up on type safety in certain areas. And since you're the one making the decision, it's usually okay to do so. Right? Oh, I know this will never happen. So instead of letting the type checker not let me write this program, I will write this program and say throw an exception if you end up in this situation ever. So since you're throwing an exception, you are still crashing your program. But since you are making these decisions, and you usually do it in rare, weird cases, most of your program ends up being type safe. So only these very high-level decisions ends up being not type safe. But since you know what your input data looks like, you're still safe in that sense. So, kind of going back to your question of what about more popular languages such as Java, they tend to be less type safe in the sense of making these guarantees, but they still have a type system, and if it type checks, it's still giving you some sort of a guarantee. So if your program, if your compiler says things type check, then it's still somewhat of a guarantee that you're probably not going to crash. So I don't know if that's like a satisfactory answer, but that's what we have.
How easy is to learn OCaml? Because I know there is a cryptocurrency that's using OCaml to do formal verification of smart contracts.
So that's a weird question to answer, but I'll tell you guys how I learned OCaml. So this was some sort of a summer break or something. Maybe I had 2 weeks off somewhere, and then I decided to go on HackerRank and try out all the problems there. And over there, I was looking at the list of supported languages, and I saw this OCaml language, and I thought, oh, I like camels, so I'll try out this language. And I just tried out the language, and that's how I learned it. So I don't think any language is that difficult to pick up. But you know, like the more you use it, the more you learn it, kind of deal. So you know, when I started using OCaml, I didn't know anything about polymorphic variants. And every time I saw them, I would kind of avoid that code base in some sense. But now that I know more about them, I can kind of read that code and kind of reason about it. So it's kind of, you know, everyone kind of grows as a programmer of a certain language as they're kind of using it more or reading it more. So I don't think OCaml is that hard to learn, but I don't know. I found OCaml, for example, easier to learn than C++, but other people might disagree. So. Any more questions before we end things?
Thank you.
Okay.